Standing waves lesson homework solutions. The first question gives us a fundamental mode of standing wave on a fixed string. We are given a function of y in terms of t, y being the displacement of the string at a point x, and x being the location of the point along the horizontal, starting from 0 here, and L is there. And also we have a function for the amplitude in terms of x. The first part asks explain why the amplitude is not constant. Well, we're given that formula, so we make reference to that formula, and it's a statement of the fact that amplitude depends on x, making reference to that formula. The second part asks us to calculate the frequency of the standing wave. You should see that this function is in the form of y equals amplitude cosine omega t, which makes omega equal to 500 pi, and knowing that omega equals 2 pi f, canceling the pi and rearranging gives f equals 250 hertz. C is asking us to show that L equals 2 meters. Now, what do we know about L? We know x equals 0 here and x equals L here. We also know when x equals L, amplitude is 0. So we can use this function given relating amplitude and the displacement x. If we substitute L for x, we know that amplitude must be 0, which looks like this. And then we solve. Now we need to write an angle for sine inverse of 0. We know this is either 0 or pi or 2 pi. Looking at the location of L, L is half a wavelength, so it must be at pi degrees, because at 0 degrees it would be here, at pi degrees would be here. So I'm going to use pi and set that equal to my L, cancel the pi's, this gives L equals 2 meters. Question number 2 asks us to state two properties of a standing wave. Any two of the factors that we discussed in the lesson could be applied in this question. Part B gives us a diagram where we have one end closed and one end open pipe. So the first part says to label with letter P the position along the pipe where the amplitude is largest. We know at a closed end we must have a node, and at an open end we must have an antinode where the maximum displacement occurs for particles, so letter P must be here. The speed of sound in the air pipe is 330 meters per second, so we have the V, and we're asked to calculate the length. First, let's add that shape. And remember that that is a quarter of a wavelength. That gives us L is quarter of the wavelength formed for this standing wave. And that gives our wavelength is equal to 4L. Now, using the wave equation and substituting the values that we know, we can solve for the wavelength, which we know to be equal to 4L, and that gives us L. Part C asks a comparison question between pipes which are closed at one end and open on both ends. Now, before I answer this question, in case you don't know what organ pipes are, here is what they look like. It's a musical instrument typically found in a church. Answering the question, now the question specifically suggests why the pipes closed at one end are better for producing low frequency notes. Low frequency means high wavelength. Remember, if a tube is open at both ends, for the fundamental, this length is half a lambda. So this wavelength would be twice the length of the pipe. If one end of this pipe is closed, that same length would be quarter of a wavelength formed for the standing wave. So that wavelength would be 4L. We have double the wavelength of this case, which means the frequency here will be much lower than the frequency here, actually half to be specific. Question number 3. Air molecules near X. X is a node, which means Due to the incident and reflected wave, there's continuously destructive interference taking place at that point. For destructive interference to be taking place between two waves, you must have a compression from one wave and a rarefaction from the other wave, which is why we say it's sometimes at the center of a compression and sometimes at the center of a rarefaction. This is the condition from the two waves which allow destructive interference at X, which makes it a node with zero amplitude. In question number 4, we are given the fundamental frequency with an organ pipe closed at one end is F. And what is the fundamental frequency of an organ pipe that is open at both ends? In such questions, I like making sketch diagrams. So if one end is closed, fundamental frequency 1F. If both ends are open, the fundamental frequency is unknown. The link between the two is the fact that they have the same length. Now, if this forms at 1F, where lambda is 4L, this forms when lambda is 2L. You can see that wavelength here is double the wavelength there, which means frequency here must be double the frequency over there, which gives us C. I can only say this because the speed of the wave is constant. So I'm basically using this relationship. Constant speed, well, it's in the same medium, they both move in air. Double wavelength must have half frequency. Number 5 is pretty straightforward. It relates to the definition of the standing wave, or the differences between standing waves and traveling waves we discussed in the lesson. Answers A. Question number 6 gives us an organ pipe which is closed at one end and open at the other. The fundamental is 330, the frequency of the second harmonic. I have to say there's a flaw with this question because this should be saying third harmonic, which can get confusing. So you might remember the pattern of one end closed pipes, that they go 1F, 3F, and 5F. So if you remember that, you immediately know the answer is D. But for the sake of explaining why, let me show you how it works. This length, that's how the fundamental frequency would look. And the next one, having a node here and an antinode here, would look like this. If that's the length of the pipe, that wavelength is 4L, and that wavelength is 4/3 of L. And this means that if the frequency is 330 here, you can see that this is 1/3 of the original wavelength. So the frequency must be 3 times the original frequency, which gives 990 Hertz. Question number 7 gives an organ pipe of length L open at one end. This is how the fundamental frequency would look, and this is how the next one would look. You must have a node here and an antinode here. Therefore, once you draw this picture, you realize this is 3/4. So you write for the second harmonic, L is equal to 3/4 of a wavelength, which means wavelength is 4/3 of L. That answers the question.